Hello all, welcome back to our deep learning series. In the previous episode, we understand what a neural network is, how it is inspired by the human brain, and where deep learning is used in real world application. In this episode, we are going one step deeper. Today, we will understand how deep learning actually recognizes handwritten digits. We will use a very famous dataset called MNIST, which contains handwritten digits from 0 to 9. For example, when we see this digit, we immediately say it is 8. But a computer does not see it like a human. A computer sees numbers. Every image is converted into pixel values as we discussed earlier. And those pixel values are passed into a neural network. Let us start with a simple question. How does deep learning recognize a handwritten digit? Here we are using the MNIST example. The full form of MNIST is the Modified National Institute of Standards and Technology Dataset. It is a famous dataset of handwritten digits from 0 to 9. Total, we have 70,000 handwritten examples. In it, 60,000 we are using for training the model and 10,000 we are using for testing the model. So each image is usually represented as 28 by 28 grayscale image size. Now look at the left side of the slide. We can clearly see a handwritten digit 8. As humans, we directly understand the shape. We see the top loop, the bottom loop, and we say this is 8. But the neural network does not see an image like this. It does not think this is a curved line, this is the upper part, this is the lower part. Instead, the image is converted into numbers. Since the image is 28 pixel wide and 28 pixel tall, the total number of pixels is 784, which is 28 multiplied by 28. So one image becomes 784 input values. Now look at the center part of the slide. Each cell in this grid represents a pixel. In a grayscale image, each pixel has an intensity value. Usually 0 means black, 255 means white, and a value between 0 and 255 represent different shades of grey. So the handwritten digit is not directly given to the neural network as a picture. It is given as a long list of numbers. For example, pixel 1 has some value, pixel 2 has some value, pixel 3 has some value, and this continues up to a pixel 784. Now look at the right side of the slide. These 784 pixel values are passed into the neural network as an input. The network contains hidden layers. These hidden layers try to learn patterns from the pixels. In early layers, the network may learn simple patterns like what small stroke or edges. In deeper layers, it may learn more meaningful digit shapes. Finally, the output layer has 10 possible solutions. Starts from 0, 1, 2 and 9. The network gives a score or probability for each digit. The digit with the largest score becomes the prediction. In this example, the output is 8 is highlighted, so the predicted digit is 8. The key idea is very important. Deep learning does not see a digit like a human. It sees pixel values, learns patterns from many examples and predicts which digit is most likely. This is the same basic idea used in image recognition, face recognition, medical image analysis, object detection, and many other computer vision tasks. Now let us understand the simplest building block of the neural networks, that is perceptron. In episode 2, we compared a biological neuron and an artificial neuron. Now we are looking at the artificial neuron more technically. A perceptron takes input values, multiply them by weights, and it adds a bias to it and computes a weighted sum, and then it passes through the result through an activation function to produce an output. Let us break this slowly. The input values are the data given to the perceptron. For example, in the MNIST digit example, the inputs are pixel values. Next, each input is multiplied by a weight. A weight tells the model how important that input is. For example, in digit recognition, some pixels are more important than others. Pixels that are part of the digit shape are more useful than pixels in the empty background. The model learns this importance using weights. Then we add a bias. Bias is like an extra adjustable value that helps shifting the decision boundary. It gives the model more flexibility. Like in a straight line equation, we write y is equal to mx plus c. So here plus c is the constant, that is a bias. Similarly, in deep learning also, for each layer we have a bias. After that, the perceptron calculates the weighted sum. The formula is z equals w1 multiplied by x1 plus w2 multiplied by x2 plus w3 multiplied by x3 and so on. Finally, plus bias. In compact form, we can say z equals to summation of wi xi plus b. This value z is called the net input or weighted sum. Then the activation function decides the final output. In a class perceptron, the activation function is often a step function. So if z is greater than or equal to 0, the output is 1. If the z is less than 0, the output is 0. We will discuss more about the activation function in the next episodes. So that's why classical perceptron is mainly used for binary classification problems. Binary classification means only two possible classes. For example, spam or not spam, dog or not dog, class 0 or class 1, yes or no, these kind of questions. On the left hand side of the slide, you can see two groups of points. The perceptron tries to draw a straight line that separates one class from another. This line is called a decision boundary, like a binary classification example. Now we come to the most important question: how does a perceptron learn? Learning means improving the weights and bias so that the prediction become more accurate. This learning process has four main steps: forward pass, loss calculation, backward pass, gradient descent update. Let us understand each step carefully. Step 1 is the forward pass. In the forward pass, the model takes the input value and calculates the weighted sum. The formula is same as we discussed in the previous slide. Z equals to W transport X plus B. This means we multiply the input with their weights and add them together and then add the bias as discussion in the previous slide as mentioned. After that, we apply an activation function. The prediction is written as y hat equals to sigma of z. Here y hat means the predicted output, sigma is the activation function. For training, we usually use a differentiable activation function because we need gradients to update the weights. In deep learning, gradient calculation is very important. Now let's come to the second step, loss. Loss tells us how wrong the prediction is. If the true answer is 8, but the model is predicted 3, the loss will be high. If the model predicts 8 with high confidence, the loss will be low. For binary classification, one common loss function is binary cross entropy. The formula L equals negative of y log y hat plus 1 minus y log 1 minus y hat. Do not worry if the equation looks difficult. The simple meaning is this: loss measures the distance between the predicted and the correct answer. The goal of training is to reduce the loss. Step 3 is the backward pass. In the backward pass, the model calculates how much each weight contributed to the error. The error can be written as delta equals y hat minus y. Here y hat is the predicted value, y is the true or original value. Then we calculate the gradient for each weight. So we are differentiating it. Differentiation of L by with respect to Wi, which equals to delta times xi. This tells us how changing a particular weight will affect the loss. But for the bias, we are doing again differentiation. dl by db equals to the delta. This predicts the basic idea behind backpropagation. Step 4 is a gradient descent update. Gradient descent update the weight and bias in the direction that reduces the loss. The weight update, the formula is Wi becomes Wi minus eta times dl by dw1. The BIOS update, the formula is B becomes B minus eta times dl by db. Here the new parameter eta is called the learning rate. The learning rate controls how big a step we take during learning. If the learning rate is too small, learning becomes very slow. If the learning rate is too large, the model may jump too much and fail to learn properly. So the selection of learning rate is important. If you take a convex problem, if the learning rate is too small, so you can see it slowly jump one over the other and try to reach the goal, but the process is very slow. Let's say you have taken learning rate is too large, as I mentioned, so it will jump here and there. Sometimes there is a chance to miss to reach the goal, so that's the problem. So selection of this is very important. Finally, the training loop looks like this: forward pass, calculate the loss; backward pass, update your weights, and repeat this process for as many examples what we have in the training data. Over time, the model adjusts its weights and bias so that the predictions become better. The same idea extends to deeper neural networks. When we have many layers, the backward pass is applied across all layers. That is called backpropagation. The key takeaway is learning means adjust weights and bias to reduce prediction error. And gradient descent updates the model step by step until predictions improve. Now let us understand the prediction with very simple visual example. Here our goal is to classify animals into two groups, dogs and horses, as shown in this slide. Imagine we have some data points, each point represents an animal. The position of the point is based on two features x and y. For example, x could represent one feature, y could represent another feature. In real machine learning problems, features may be measurements, pixel values, word values, sound values, or other numerical data. In the first panel, there is no decision boundary. The model has not learned anything yet. It does not know how to separate dogs and horses. In the second panel, the model draws a line, but the line is not good. Some animals are on the wrong side of the line. So the model makes mistakes. Here the error is 2 because two animals are misclassified. In third panel, the line becomes better. Now fewer animals are misclassified. Here the error is 1. In the fourth panel, the model finds the best decision boundary. The line separates dogs and horses correctly. Here the error is 0. No animals are misclassified. This is the basic idea of learning. The perceptron tries to adjust lines so that the classification error becomes smaller and smaller. In mathematical terms, the line is controlled by the weights and bias. When the perceptron updates weights and bias, the decision boundary moves. So learning is not magic. It is repeating process of prediction, error calculation, and weight update. But one important limitation is this: a single perceptron can only learn a straight line boundary. It works well only when the two classes are linearly separable. A linear separable means we can separate the classes using one straight line, but many real world problems are not that simple. Images, speech, text, and videos usually need complex boundaries. That is why we use multiple neurons and multiple layers. When many perceptrons are connected together, they form a neural network. A neural network can learn much more complex patterns. Now it's a quiz time. Pause the video and write your answers in the comment section. Question number 1. In the MNIST example, what does the neural network actually receives as input? Option A, the digit name written in the text. Option B, pixel values from the 28 by 28 image. Option C, a fully color video. Option D, only the final label. Question number 2. What does gradient descent do during learning? Option A, it updates weights to reduce the loss. Option B, it randomly changes the labels. Option C, it converts image into videos. Option D, it removes all hidden layers. Write your answers in the comment section. Let us see how many of you got both answers correct. For question number 1, the correct answer is B, pixel values from the 28 by 28 image. So because as I mentioned, the neural network does not directly receive the digit as a human readable image. It receives the numerical pixel values. In MNIST, each image is 28 by 28 pixels, so one image becomes 784 input values. Okay, for question number 2, the correct answer is A. It updates weights to reduce the loss. As we discussed, gradient descent adjusts the weights and bias step by step so that the model's prediction error becomes smaller. That's all for this episode. In the next episode, we will learn about activation functions and how to define model layers in Keras. This will help us move from theory to practical deep learning model building. If this video helped you, please like, comment, share and subscribe. Also, do not forget to write your quiz answers in the comments. Thank you for watching. Have a good day.